Hi, this is the Start 3D Modeling channel, and in this video I will show you how to start working with Plasticity. Plasticity is quite a new but rather interesting 3D modeling software. It is software that more and more users are using each year. The software is constantly being developed and is available at quite an affordable price compared to other 3D CAD systems. When it comes to 3D modeling in Plasticity, we have an approach based on direct modeling here. It is not the typical 3D modeling known from popular 3D CAD systems, in which the 3D modeling approach is based on features and parameters. In the case of typical technical 3D CAD systems, we model parts using features and parameters, and the 3D modeling is based on an operation history. In the case of Plasticity, we don't have parameters and we don't have an operation history. Everything we do is done directly in the workspace, and even though, as I say this, it may seem like a drawback, in many cases it is a huge advantage. It will certainly be an advantage for people who are not engineers, who design as a hobby, for example for 3D printing, and in my opinion many things can be done more easily in Plasticity than, for example, in FreeCAD or Fusion. Of course, to confirm this, it is worth getting familiar with other systems. It is worth getting familiar with FreeCAD, Fusion and Plasticity. This will definitely make it easier to make a decision. On my channel you'll find videos showing the basics of working in Fusion and Plasticity. I simply want to show how we create 3D models in different programs so that everyone can decide which program to use. As for Plasticity, it is not free software, you have to pay for Plasticity. However, the price of this software is quite affordable, and when it comes to Plasticity, we have two versions, the indie version and the studio version, and we can take advantage of 30-day trial period. Simply by going to the website plasticity.xyz, we can download the installation version for our operating system. As you can see, we can use Plasticity on Windows, Mac and Linux. What's more, we can use Plasticity on several computers, and the number of computers on which we can install Plasticity depends on the license. When it comes to Plasticity licenses, apart from the 30-day trial in which we can test the indie version, we have the indie version and the studio version. At the time I am recording this video, the indie version costs $150, but soon the price will be increased to $175. Regarding the increase in software prices, the developers are very transparent about it. The software uses Parasolid, which is a sort of component that forms the base of the software, and many different 3D CAD systems use it, and the developers of Plasticity have to pay for the Parasolid license themselves, and I think this could be one of the reasons for the price increase. Of course, the fact that the software is constantly being developed and worked on by the developers also has an impact, and this can be observed on the Plasticity Discord. After purchasing either the indie or studio license, we get access to a private Discord channel where beta versions of Plasticity are regularly published and studio license holders can use them. And so when it comes to these two versions, they are paid versions of Plasticity and they can be used commercially, and as you can see, 150 for commercial software is not very much. Even 300 is not a huge amount because it is a perpetual license. Once we buy such a license, we can use Plasticity forever. After purchasing the license, we have 1 year of support, and for 1 year we receive software updates, and after those year we stop receiving updates but can still use Plasticity. So if you decide that Plasticity in its current state suits you and you don't need new features or updates, you don't need to renew the license. Of course, renewal is slightly cheaper than the full license price. I will get to that in a moment, but here I would like to talk about the differences between the indie and studio versions. And as for the indie version, we have solid modeling tools here. For most people, this should be more than enough, and this version can be installed on 2 computers. In this case, the Indie license allows one person to use Plasticity, but that one person can use it on 2 computers. With the Studio license, we can install this version on 4 computers. Of course, Plasticity is limited to use by a single user, but in this case, we can use it on 4 computers. So, for example, if you work at home, in the office and in the workshop, you can install Plasticity on each of those computers, and as long as you are the one using Plasticity and not someone else, you are doing it completely legally. And here the price differences is not only due to the fact that we can install this version on a larger number of computers. In addition to having solid modeling capabilities and the Parasolid kernel, we also have something called Xnerps. As you can see, we can only use this on Windows and Mac. The Xnerps module is a surface modeling module that is also used in other 3D CAD systems, and often the Xnerps add-on alone costs more than $300. That's why if we look at the individual components of the Studio license, the price doesn't seem excessive. What's more, and I will emphasize this again, these licenses are perpetual. We can use this license lifetime. The only limitation is that we receive support and updates for 1 year. Of course, we can renew it on slightly more attractive terms, but we don't have to. I will now move on to the costs of renewing such a license. And when it comes to renewing the Indie license for another year, we pay $100 plus taxes. And when it comes to renewing the Studio license, we pay $175 plus taxes. And when it comes to upgrading from the Indie version to the Studio version, we pay $200, and in doing so, we get the upgrade and another year of support. And if you would like to purchase Plasticity, you click Buy Now. And during the purchase, apply the discount code DamienCADCAM and the price will be reduced by 10%. So here with taxes in Poland, the price is $331. Whether this is a lot or a little, everyone has to decide for themselves. For me, even though it is a significant amount, compared to other 3D CAD systems, it is an affordable price for this type of tool. But okay, that's it for the introduction about Plasticity licenses. I used the Indie version for a year. Now when renewing my license, I switched to the Studio version. I haven't yet delved into surface modeling because I don't deal with it, but I do want to check out these tools. I want to see what surface modeling looks like in Plasticity. In this video, I will focus mainly on the tools available in the Indie version, and these tools are also available in the trial version. So if you want to see what working with Plasticity looks like and want to learn some basic 3D modeling operations, download the trial version and you can follow along with this tutorial. Okay, after launching the Plasticity, you will see this window. This window is divided into 3 parts. In this part, we have the outliner. This is where the geometries we created will appear. Then we have the main workspace, and then on the right side of the window, we have various controls that we can turn on or off and switch between during work. As for these side panels, we can hide them and then the workspace will increase. And when it comes to creating 3D models in Plasticity, as I mentioned, we have an approach based on direct modeling, and here everything we do is done in the workspace. We will start by creating a simple shape. We will create a rectangle, and when it comes to drawing a rectangle, we have several options available here. At the moment, the corner rectangle command is active. However, with this command, we have a small arrow, and if you hover over this command and press and hold the left mouse button, other commands will appear that allow you to create a rectangle. Select the center rectangle command here, and to select this command, hover over it with your mouse cursor and release the mouse button. Now this command is active. And as you can see, next to the cursor we have a snap, and snaps make it easier to create geometry. At this point we need to specify the center point of the rectangle, and I would like to place this point at the origin of the coordinate system. And as you can see, when I hover over this point, there is an active snap at the origin of the coordinate system. And when it comes to snaps, we have a section here called snapping. If we turn this off, there are no snaps anymore, and now I can no longer precisely define the position of the rectangle's center point at the origin because I don't have an active snap here. If I turn the snaps back on, I can place the center of the rectangle at the origin. To do this, we hover the cursor over this point and click the left mouse button. Now we can draw the rectangle, and I would like to draw this rectangle with specific dimensions, for example 200 by 50 millimeters. We can try to do this by dragging the cursor. However, as you can see, even though the dimensions are displayed, it's difficult to precisely catch those values, but while drawing geometry we can enter dimensions manually, and to do this we press the Tab key, and here we can specify the dimensions. I type in 200, press Tab again to switch to the second dimension, then type in 50 and press Enter to confirm. This way we have created a rectangle. At this point it is flat geometry, and based on this flat geometry we can create a 3D solid. However, before we do that, I will briefly discuss navigation in Plasticity. And to rotate the view, press the mouse wheel, and while holding it down we can move the mouse to rotate the view. To zoom in and out we use the mouse wheel by scrolling it. This way we can zoom in and out of the view. If you want to pan the view, press both the left and right mouse buttons at the same time, and then you can move the view. Next important thing in Plasticity is the geometry selection modes. We have modes for selecting points, edges, faces and solids. At the moment, 3 modes are active, but we can activate each of them individually. We simply click left mouse button on the appropriate selection mode, and now the solid selection mode is active. However, in the workspace we don't have any solids, so I can't select anything here. If we activate the face selection mode, meaning we can select faces, I can select the area of the rectangle here. If we choose the edge selection mode, we can select flat geometries and solid edges. And when we choose the point selection mode, we can select points and vertices. We can also activate these modes by pressing the corresponding keys on the keyboard. Press 1 to activate the point selection mode. Press 2 to activate the edge selection mode. And press 3 to activate the face selection mode. Press 4 to activate the solid selection mode, and press 5 to have all modes active. When working with Plasticity, using the keyboard greatly speeds up 3D modeling. Many commands can be activated by using keyboard shortcuts, and when working in Plasticity, it's worth learning at least the basic and frequently used shortcuts. Now I will switch to the face selection mode, and based on this rectangle I want to create a solid. I have just switched to face selection mode so I can select the area of this rectangle to create a solid from it. Here, as you can see, the extrude operation was automatically activated. And for selected operations to be triggered automatically, we must have the option enabled in the settings. This is an option in the General tab. Here we have the setting that allows selected commands to be activated automatically. This option is enabled by default. If it is not enabled for you, you can turn it on or you can simply call commands manually. If you want to activate the extrude command, select the geometry and then from the list of commands either choose extrude from here or open the list of all commands and type in extrude and activate it. Now, since we are on the topic of commands, here on this toolbar we have several basic and frequently used commands. Here we have a longer list of frequently used commands, and by clicking this icon we have a list of all available commands. We can activate this list anywhere in the workspace by simply pressing the F key. Then we have access to all commands. We can type the name of the command, press enter, and that command will be executed. The extrude command works so that based on the selected geometry, we can create a solid by pulling that geometry out. We can do this freely to any value, or we can precisely define the extrusion distance. For example, here in the distance field, we enter the value, or while creating the extrusion, we can press the D key and type a specific value from the keyboard. In this way, we can create a solid by extruding the selected geometry to a defined value. In this case, we created a solid with a height of 15 mm, which was generated by extruding the selected area. Here, as you can see, a solid has appeared in the outliner. We also have the flat geometry. Unlike in parametric 3D CAD systems, these geometries are not linked to each other, and the solid is now independent from the flat geometry. In parametric 3D CAD systems, if we made changes to the flat geometry, for example changing its dimensions, those changes would update the solid as well. For example, here I pressed the equal sign on the keyboard and entered 75 for one dimension and 250 for the other, and the flat geometry dimensions have changed, but the solid dimensions have not. This is a key difference. In parametric 3D CAD systems, solids created from a 2D sketch are linked to that sketch, so changes in the sketch are reflected in the solid. That is a huge advantage of parametric CAD systems. However, in Plasticity, we should not treat this as a disadvantage, but simply as part of the software's design. It uses a different approach to 3D modeling, which in many cases also has its own advantages. Now, going back to the extrusion operation, in the previous example, I wanted to create an extrusion based on an area. That's why we switched to the face selection mode, selected the area and created the solid. And what would happen if we had selected edges instead and then activate extrude? Based on edges, we can also create an extrusion, but instead of a solid, this produces something called sheets, basically surfaces. By extruding the edges, we created surfaces. So if someone needs to create surfaces, this is one way to do it. I will now hide or delete these surfaces. Simply select them in the outliner and press delete. Now in the workspace we have only the flat geometry and the solid, and the flat geometry is no longer needed, so we can delete it as well. Select it and press delete. And now we have only the solid in the workspace. At the moment this is nothing special, just a regular box. And regarding navigation, I use a 3D controller, a space mouse from 3D Connection, and this is not an essential device for working with CAD systems, but it greatly improves and makes working with such programs more enjoyable, and it allows for smooth navigation. I mention this because some may wonder how parts in CAD system can be rotated so smoothly, and this can be done with a space mouse. Now, regarding the model, it's nothing special yet, just a box, but in Plasticity, as in other CAD systems, we can create 3D models in stages. By building relatively simple elements and shapes, we can create a complex 3D model. In this tutorial, I will not create a complicated model, I just want to show you the principle of how such 3D models can be built. If we want to create the next stage of this model, we can either make another solid or remove material from the existing one. This time we will add another section to the solid. We will draw another rectangle. Choose to draw the centered rectangle. Now I want the center of the rectangle to be here on the top face of this solid, aligned with the z-axis, and when this snap is active, I click the left mouse button and now the rectangle's center is here. Next, I want one corner of the rectangle to lie on the solid's edge. I hover the cursor over that edge and notice that one dimension of the rectangle is 50 millimeters. I want to keep that dimension, but I want to set the second dimension to 40 millimeters. To do that, I press Tab key, type 40 and leave the other dimension unchanged and press Enter. This way we have created a rectangle with one dimension set to 40 millimeters and the other defined by linking its corner to the solid's edge. Now, based on this rectangle, we can create another solid or another section of the existing solid. The difference is that by extruding this rectangle, we can create a separate solid. If we extrude it and click OK, a second solid is created, completely independent from the first solid. And if that's what you want, you can leave it like that, but we can also simply create another section of the same solid so that it will be a single unified solid. We can do this in two ways. We can, at this stage, join the two solids together. To do this, we select both solids. I switch to solid selection mode, hold Shift to select both, and activate the Boolean operation, which allows us to join or subtract solids. We can activate this operation by clicking the icon or by pressing Q on the keyboard. Here the default option is diff, which subtracts one solid from another, but we also have the union operation, which causes the selected solids to be combined into one. Of course, for Boolean operation we can select more than two solids. And now they are a single unified solid. I press Ctrl Z to undo back to the stage where we didn't have the joined solid. And now if you want to create another section of the solid so that the extrusion we make from this geometry is automatically joined with the existing solid, we can do this during the extrusion operation. I switch to face selection mode and select the area of this rectangle. Here, as you can see, the gizmo is facing down. If you want to extrude upwards, in this case, we need to enter a negative value, but that's not a problem. I press D, type -15 and press Enter. And before finishing the operation, I check what commands are available here. And as you can see, in the bottom right corner, we have commands available during the active operation. In the case of the extrude operation, we have the union command, which allows us to join the extrusion to another solid. So now, to make this extrusion part of the existing solid, I press Q and select the solid I want to join it to. I click OK, and in this way the model becomes a single unified solid. In the outliner, I see that I still have a solid created from the previous extrusion. This solid was not deleted after the earlier operation, so I select it and press delete. And now what we made in this extrusion operation is a single solid. Step by step we can build the 3D model in stages. As for another operation, from flat geometry, we can also remove material from a solid. Now I'll switch to the top view, which can be useful. We have a cube here and we can set the view to whatever is most convenient for us. I will now create holes in this solid and I'll do it with a circle. I select the circle drawing tool and I want the center of this circle to be placed 15 millimeters from the edge of the solid. As you can see, if I draw the circle now, I can't define its position precisely. The circle is placed rather freely. And to do this, we can draw the circle starting from this point. I hover over this point, click the left mouse button, press Tab to set the circle's diameter, type 15 millimeters and press Enter. Now I'll simply move this circle 15 millimeters along the x-axis, and to do this we select what we want to move. Choose the move command. We can press G on the keyboard or select it from the menu and then move it along the x-axis by 15 millimeters. Here we can specify the movement values in this field for the x-axis, in this one for the y-axis, and in this one for the z-axis. But we can also do it in this way. After activating the move command, press X, type 15, press Enter and press Enter again to confirm. This moves the circle 15 millimeters in that direction. We can do the same on the other side. Choose to draw a circle, place it here, press Tab to set its diameter, then press G, then X. In this case, I need to move it in the negative X direction, so I type -15, press Enter and press Enter again to confirm. Now I close the construction plane and based on these geometries, we'll create holes in the solid. These geometries happen to be placed in the middle of the solid, but that's not a problem. We simply switch to face selection mode, hide the solid and select the face of the first circle, hold Shift to select the second circle's face and extrude them to any length. I turn the solid's visibility back on and I also want to extrude in two directions because as you can see right now the extrusion is in one direction from the sketch plane, but if we press Tab key the extrusion is created in both directions from the sketch plane. In this case the extrusion value doesn't matter. What's important is that the cylinders we create extend past the solid because we want to use them to make holes. Just like with an extrusion, we can create these two cylinders, click OK, and then use the Boolean operation to subtract them from the main solid to make the holes. To do this, I switch to solid selection mode. First select the solid we will subtract from, then hold Shift and select the solids we will remove. Press Q to activate the Boolean operation. The default is difference and click OK to confirm. And the holes are created. I'll now press Ctrl Z. OK, we have two circle faces. I'll add an extrusion here, press Tab, turn on the solid's visibility, and since the extrude operation is active, I check the available options. We have the difference command here, which subtracts one solid from another. This works so that the extrusion we are making can be subtracted from another solid. So I press W key, select the solid to subtract from, click OK, and in this way the holes are created. I turn off the visibility of the flat geometries, and now we have our solid. As for creating flat geometry, we can also draw it directly on a solid's face, which will then be used as the sketch plane. I switch to face selection mode, select this face and press spacebar to activate a temporary construction plane. Now we can create some geometry. I choose to draw a circle, place its center at this point, press Tab and type 20 to set its diameter. Then I close the temporary construction plane. The circle is now placed on that face. I select the circle, extrude it in this direction to any value, press W key, select the solid, click OK, and we have removed material from the solid. I know that in this tutorial we are moving very slowly. There is a lot of my commentary, but making a tutorial and modeling for yourself are two completely different things. When you model 3D parts on your own, it's much faster than following along with a tutorial. At the start, you simply need to learn the basics, the working methodology of your software, and once you start creating 3D models independently, the process speeds up significantly. On this example, I'll show you one more thing. I'll switch to edge selection mode to demonstrate adding chamfers and fillets. Chamfers and fillets are always added to edges. When you select an edge, the fillet command is automatically activated. This command lets you create a fillet or a chamfer. Whether it's a fillet or a chamfer depends on the direction you drag the gizmo. One direction for a fillet, the other for a chamfer. But we can also do this faster and more precisely. Holding Shift, I select these two edges. Let's say I want to add a fillet. The fillet command activates automatically, and we have additional options here, fillet distance and chamfer distance. If I press D, type 10, press enter and then enter again, the fillet is added. Now I select this edge, hold Shift to select another, press C, type 10, press enter and enter again, and now the chamfers are added. As you can see, adding chamfers and fillets in Plasticity is very quick and efficient. Even better, we can add chamfers and fillets to all edges of a solid at once, and to do this, select the solid, then convert the selection from solid to edges with Ctrl+2. The solid selection is converted to edge selection and the fillet command is automatically activated. Now I press D, type 1, press enter, then enter again, and the fillets are applied to all edges. That was a simple example to show you the most basic commands available in Plasticity. Before we move on to more 3D modeling operations in Plasticity, I want to show you an important and useful feature related to 3D modeling. As I mentioned earlier, Plasticity is based on the Parasolid kernel. This is a kernel used in various 3D CAD systems, which means that in Plasticity we can save 3D models in the Parasolid format, specifically in the XT format. This format is quite common in professional 3D CAD systems, and such files can be opened, for example, in SolidWorks. In addition, Plasticity also allows saving 3D models in the STEP format, which is a universal data exchange format between 3D CAD systems. This means that if you create a 3D model in Plasticity, you can save it in the STEP format, and someone else using a different 3D CAD system can open it on their end. So, if you use Plasticity commercially, meaning you want to earn money from your models, you can save 3D models in formats supported by other CAD systems, which makes collaboration with others much easier. And to export a 3D model to STEP or Parasolid format, go to the Plasticity menu and choose Export. When exporting, you can either export a single model or export multiple models into one file. In this case, we have only one solid in the project, so only this one will be exported. But if you had multiple solids, you could select one to export, or if you don't select anything, the entire project will be exported, meaning all solids will be included in the chosen format. We select export, choose the location and file name, and select the format we want to export to. In the format list, we have a Parasolid XT, a good format for CAD data exchange, but not all CAD systems support it. And we also have Step, which is also very good for CAD data exchange, and most CAD systems support Step. So if you save the file in this format, it's very likely that someone using another CAD system will be able to open it. Typically, most popular and well-known CAD systems support Step, so we'll select this format and click Save. Next, we choose the Step file variant. There are 3 types. The differences is in the kind of data transferred in each. AP203 is the simplest format and I recommended starting with it. That said, I've also had no issues opening files saved in the other formats in various CAD systems. If you are curious, you can look up what data each step format contains by searching for step AP203 or step AP214, and you will likely find a comparison explaining the differences in the first search results. We click OK and the model is exported as a step file. We can now open it in another CAD system. I'll open it in Fusion, and the model we created in Plasticity is now available in Fusion. For the person opening the file, it doesn't matter which system it was created in. They can simply open it and use the model in their own project. What's more, the step format is now also supported by slicers, software used to prepare machining programs for 3D printers. So if you design parts for 3D printing or models to share on various websites for 3D printing, you can also do this in Plasticity. You can share such 3D models in STEP or STL format. STL is a format commonly used in 3D printing, but it stores the model as a mesh of triangles rather than a solid, which makes later editing much more difficult. Nowadays, STEP is also often used for 3D printing, and in my opinion, it's a better format for this purpose. And in Plasticity, we can export models directly in STEP format. Now I'll switch to Bamboo Studio to show you this in action. I open Bamboo Studio and add the model here, and the model we created in Plasticity has been imported into Bamboo Studio. So as you can see, if we use Plasticity, we have great possibilities for collaborating with other people. Okay, I'm going back to Plasticity, and now we'll move on to the next 3D modeling operations. I'll create a new project. As for me, I am a user of 3D CAD systems designed for technical modeling, where models are usually created with precise dimensions and rather regular shapes. In this part of the tutorial, I'll show you how we can handle specifying exact dimensions and the exact position of geometry. I touched on this partially in the previous example, but now as an exercise, we'll make another simple example in which we'll focus on creating 2D geometry with precise dimensions and precise positioning. I'll switch to the top view and start by creating a rectangle, for example 200 by 100 millimeters, with its first corner at the origin of the coordinate system. We choose the rectangle drawing tool, make sure snapping is active, and to place the first corner of the rectangle at the origin, we simply click here with the left mouse button. Then to set the rectangle's dimensions, we press Tab, type 200, press Tab again, type 100 and press Enter to confirm. This creates a rectangle of 200 by 100 millimeters. And as you can see, these dimensions are not displayed. I click the left mouse button to deselect the geometry and switch to edge selection mode. And when it comes to 2D geometry, after creating it, we can change its dimensions. To do this, we select the geometry and press the equal key on the keyboard. And now we can enter different dimensions and they are updated. However, as you can see, the rectangle's position also changed because I changed the dimension from 100 mm to 150 mm. The rectangle grew in that axis symmetrically in both directions. And if you want to move this geometry so that the corner of the rectangle lies exactly at the origin, we can do it easily with the move command. Here you can shift it along y-axis by entering a specific value, but to do this precisely, we must enter the exact value in this field. In this example, we happen to know the offset value, but sometimes you won't know it. That's when we can use the freestyle option. Press F key on the keyboard, then select a reference point, select this corner, and then select the target point to which we want to move the geometry. I'll show you again how this works. I'll move this geometry to any position, right click to confirm, then with the rectangle selected, I press G to activate the move operation, press F to activate freestyle mode, select the reference point, then select the target point, and click OK to confirm. I know this is a simple example, but it's a very useful option. Once you start making more complex 3D models, you'll see just how helpful and practical it is. Now, regarding creating precise shapes, as you can see, when I draw some geometry, I tend to place it quite freely without defining its position. In typical technical 3D CAD systems, when drawing, for example, a circle, I can also define its position relative to some other geometry. I can define relationships between geometries. In Plasticity, we don't have that in the same way as in parametric CAD, although we can still add dimensions between geometries and later modify those dimensions. We'll get to that shortly, but first I want to show you some ways we can handle creating such geometry. One of them I already showed in the previous example. Simply create the geometry at some specific point. For example, I'll create a circle with a 15 mm diameter at this rectangle's corner. I set the circle's center at the corner, press Tab to define its diameter, type 15 and press Enter to confirm. And now I want to move this circle so it is offset by 15 mm in the negative X direction and 15 mm in the negative Y direction. To do this, I use the move command. Select the geometry, press G to activate move, and if we want to move in two axes at once, simply enter the X offset -15 and the Y offset also -15. Press enter, then enter again to confirm. This way we have positioned the circle precisely. Another way is to use construction geometry. For example, I can create a line starting from the midpoint of this edge. As I hover near the midpoint, a snap appears indicating the edge center. I click there and draw a line 40 mm long in this direction. Drag the cursor, press Tab, type 40 and press enter. I can now use that geometry as a reference, for example, to draw a rectangle with one corner at that point. I draw the rectangle with dimensions 40 by 20 mm. Then I can delete the helper line, select it, press delete, and still have the rectangle precisely positioned. Another way to set exact positions is by using dimensions. For example, I draw a circle of any diameter and I want it offset from the origin, this rectangle's corner, by 30 mm in X and 25 millimeters in y-axis, I can use the measure distance command. First, measure from this point to this point in the x direction. Then measure from this point to this point in the y direction. And now, to change one of those dimensions, I select the geometry, press G for move, click on the dimension I want to edit, type the new value, and press Enter. If I want to change the second dimension, I repeat the process. If I want to change the circle's diameter, I press equal sign on the keyboard and enter the new value. The equal commands corresponds to the dimension tool, which can also be found in the command list. This is how we can set precise geometry positions in Plasticity. Moreover, in Plasticity we can also change the position of features already created on a model. Based on this sketch, I'll create a solid 15 mm high. Press D, type 15, hit enter and enter again to confirm. I'll hide the flat geometries using the eye icon. They are no longer linked to the solid. If you select multiple items with Ctrl, you can hide or show them together. Let's say I want to change the diameter of a hole. I switch to face selection mode, select the hole's face, press equal sign on the keyboard and enter the new diameter. If I want to move this hole, I add dimensions, for example from the hole center to the rectangle corner along the x-axis. Then I select the hole's face, press G for move, click the dimension and enter the new value. This works for moving and editing any feature on a model, even features on models created in other CAD systems. For example, if you have a model from Fusion saved as step and want to modify it in Plasticity, you simply select the feature, change its size or move it. If you want to enlarge a rectangular pocket, select one face, use push face to move it freely, or press D for precise value, say for example -10, and then confirm. If you want to move the entire pocket, add a dimension, for example from this point to this point in x-axis, then select all 4 faces of the pocket, select it with Shift key pressed, then press G, click the dimension and enter a new value. As you can see, this makes it very easy to make such changes. This is a huge advantage of direct modeling. Everything is done directly on the 3D model and we have tremendous flexibility to edit both models created in Plasticity and those imported from other CAD systems. I want to emphasize this capability. I've had cases where I received step files and needed to make small adjustments like moving a hole, changing its diameter or adjusting pocket depth. In parametric CAD, at the time I was using SolidWorks, it wasn't as quick as in Plasticity. So if you ever need to modify a step file in Plasticity, you can do it quickly and easily. Now we'll move on to another simple 3D modeling operation, one that allows us to create a 3D model by rotating a sketch around a selected axis. And this is how we can create a revolved solid. I'll start a new project and make a half profile of such a solid. I'll switch to the side view on the XZ plane and draw a very simple shape, a rectangle of any dimensions. And based on this rectangle, we'll create a solid by rotating it around the Z axis. Just like with extrusion, what we have selected is important. If I'm in edge selection mode and have an edge selected, and then choose the revolve operation. Next, we have to define the axis of revolution, and we do this by selecting 2 points along the axis. I'll show you this again in a moment. Here we can set the rotation angle, for example, 270 degrees. And as you can see, this doesn't create a solid, but rather surfaces based on the edges. If I click OK, in the Sheets group a surface object appears. I'll turn off its visibility and now switch to face selection mode. I'll select the geometry from which I want to create a solid by rotating it around a selected axis. Now I choose Revolve again, define the axis of revolution by picking 2 points on the Z-axis and confirm. If I pick different points, the solid is generated differently and I can see the preview. To make a full solid, I can set the angle to 360 degrees or choose another value for partial shapes. Of course, I can use any profile shape. Here I'm keeping it simple just to show how the operation works. We can also use Revolve to remove material from a solid. For example, I create a circle of any diameter. Holding Shift, select both halves of the circle because it's divided by the rectangle line. Choose Revolve. Define the axis as before and confirm. Now we have 2 separate solids. If I want to create a groove by subtracting one from the other, I switch to solid selection mode. First select the solid I want to subtract from, then with Shift key pressed select the solid to subtract, press Q for the Boolean operation, keep div as the operation type and confirm. This produced the groove. I'll start another project for a similar example. I'll draw a rectangle, for example, with dimension of 50 by 70 millimeters. And then draw a circle with its center on one rectangle edge, 30 millimeters in diameter. And here's another useful tool for 2D geometry. Trim command, it removes unwanted geometry segments. You can activate it from the toolbar or by pressing T. I select the segment to trim, click OK, and now I have the profile for the revolve. For the axis, I don't have to use the coordinate system axis. I can draw my own helper line and use that. I select the geometry, choose Revolve, define the axis by picking 2 points, set the angle and confirm. A simple operation, but in some cases extremely useful. As you already know, we can build solids in Plasticity in stages, combining different modeling methods in one model. For example, I'll start a new project, draw a rectangle and extrude it into a solid. Then I can add another part of this solid using Revolve. I draw a circle on this face, but if I revolve it now, I get something I don't want, so I cancel. I select the circle, press G for move, then F for freestyle mode, and using helper lines I move the circle exactly to the place I need. Hovering over a point, pressing Shift to enable helper lines, finding their intersection and clicking. Now I select the circle's face, choose Revolve, pick 2 points on the helper line to define the axis and confirm. This creates a second solid which I can merge with the first. Select both solids with Shift key pressed, press Q, choose Union and confirm. If I want to clean up leftover geometry lines, I select the solid, press F for the command search, find delete redundant topology and run it. And the extra line disappears. As you can see, in Plasticity we can build 3D solids in stages, mixing different modeling operations at different steps. Now I will show you another interesting operation. This will be the operation of extruding a profile along a path. First, we will create the profile shape and create a polygon. I will switch to the top view, and when it comes to creating polygons, we have a command here that allows us to create polygons. We select this command and specify the starting point of the polygon. Next, we specify the number of sides of the polygon and the diameter of the circumscribed circle. The number of sides can be set by holding down the Shift key and scrolling the mouse wheel, or by pressing the Tab key. We switch to the field where we specify the number of sides and enter a specific value. And when it comes to specifying the diameter, we press the Tab key again and enter the diameter of the circle. And this way we have created a polygon. Now we will create the path along which we will extrude this profile. We will do this using the line command. We select the line drawing command and draw a path. Let's create a simple shape, for example, something like this. Now I switch to point selection mode. I select this point and press the B key to activate the fillet command, and I add a fillet here. OK, now I switch to area selection mode and I want to create a solid by extruding this area along this path. The sweep operation allows us to do this. We select this operation, select the path along which we want to extrude the profile and click OK. And in this way we can create a solid formed by extruding a sketch along a path. As for the sweep operation, we have several additional parameters here, and I will show you this in another example. I will create a rectangle here. something like this. Now I will create a line. Okay, I select the area, choose the sweep operation using the keyboard shortcut Shift+P, and select the path along which I want to create the extrusion. And here we also have a parameter called twist. This parameter can also be useful in some cases, as we can create such an extrusion with a rotation. I deliberately used a simple example here so that it's clearly visible. And the second parameter we have here is the scale parameter, which also allows us to achieve interesting effects. For example, let's set the scale to 0.1. And we get such a solid. We click OK, and as you can see, from two simple shapes we created quite an interesting solid. Of course, the twist parameter can be used in more complex cases. It will also work when the path is more complex. And here we have the twist parameter, and we can also use it. Similarly, we can use the scale parameter. As for the distance parameter, here, for example, we can shorten the length of the extrusion, and that's how it works. And as you can see, it is a simple operation, but it can produce interesting results. Another interesting operation is the Loft operation. This operation works by creating an extrusion through multiple profiles. And to do this, we need to create several profiles. First, I create a circle with a diameter of 70 millimeters. Then let's create a polygon. It can be a hexagon with a diameter of 100 millimeters. And finally, let's create a rectangle, more or less like this. Now I will move these sketches to different levels along the z-axis. I select the rectangle sketch, press the G key, and move it 70 millimeters along the z-axis. Okay, now I select the polygon and move it 40 millimeters along the z-axis. Okay, I switch to area selection mode. Hold Shift, select these three areas and choose the Loft operation. And based on these profiles, a solid was created by extruding through these profiles. Again, by using simple and basic shapes, we can achieve interesting results. Of course, this was a quick, simple example, but for this operation you can use more profiles and get really interesting results. And while we are at it, I'll show you another interesting operation. This is the hollow solid operation, which allows you to create something like a shell or a container. It works by selecting one or more faces to remove. We choose the hollow operation and then specify the wall thickness. In this case, we will specify the thickness inward, but as you can see, this way we can create a solid that is hollow inside. Now we will perform a section analysis. I switch to the side view, enable the section analysis option, and in this way we can examine the cross section of this solid. As you can see, the solid is hollow inside. Okay, and now I will create a simple solid to show you how this operation works on a basic shape. I will simply create a cube, and here's how. We select a face, choose the hollow operation, and on a simple shape it's clearly visible. As you can see, we can specify wall thickness outward or inward. If we specify the thickness inward, we enter negative values. If we specify it outward, we enter positive values, and in this case, of course, we are enlarging the solid. and we can specify offset value, and here for example I will enter -3 mm and press enter, and now the wall thickness of this solid is 3 mm. I will now press Ctrl+Z, and for this operation we can select multiple faces. We can select for example 2 faces, we choose the hollow operation, and now those 2 faces will be removed, and that's how we can very quickly create this type of solid. Let's go back for a moment to the sweep operation. As you have already seen, this operation works in such a way that we have a profile, and let's create a path here. This path can be in almost any location. That's why I will move this path a bit to this side. The path doesn't have to touch the profile. I usually prefer to do it in such a way that the start of the profile is in the middle of the profile. Sometimes there are situations where if the path is in a different place, there may be a problem performing this operation. But even if the path is in another place, the operation should still work. I select the profile, select the sweep operation, select the path, and here we have something like this. And as you can see, the path is in a different place than the profile, and in this case it worked. Now I will move the path to another place and we will see how it looks. Let's move it this way and this way, okay. And this is how the sweep operation works. We simply select the profile to be extruded, choose the operation and select the path, and here as you can see the path is in a completely different location and the operation could not be completed. That's why I prefer to do it so that the path starts somewhere on the profile, and we will do it this way. Okay, here I accidentally hit this path. I turn on the path's visibility, select it, activate the move operation, press the F key, select this vertex and move this vertex to this point. Okay, and now I can perform the sweep operation. And here everything works correctly. Sometimes you may encounter a situation where the profile is quite large and the path is small, and in this case a kind of self-intersecting solid will be created. Let's see how this will turn out in this situation. Okay, and here we cannot do it, and that's simply because the profile is too large and the radius of this path is too small. So there is simply a problem creating the solid. Okay, here I just wanted to show you a few of these things. But a similar operation to sweep is the pipe operation, and this operation only requires a path to work. With this operation, we can create a certain variant of a solid that could also be made using the sweep operation. And to use the pipe operation, we select the path, choose the pipe operation, and we can activate it by pressing the P key on the keyboard. And here, as you can see, such a solid was created. By default, a round cross section is selected, but we can increase the number of vertices. And here, for example, we can enter 8 vertices and something will be created that we could make with the sweep operation, where the profile to be extruded would be an octagon. So if you want to create a regular shape, you can also do it using the pipe operation. Here too, we have the twist parameter, the scale parameter, and the distance parameter, so it works very similarly. Therefore, if you want to create a sweep operation based on a regular shape, you can do it with the pipe operation. However, if you think that because there is a pipe operation, the sweep operation becomes useless, I will point out right away that the sweep operation is very useful because in the sweep operation we can create a solid by extruding a profile of any shape. I showed you the sweep operation based on a profile that was a regular shape, but the purpose of the lesson was simply to show you how this operation works. However, in this operation we can create a profile of any shape. For example, let's create a rectangle. And here create some additional shape. Okay, and based on this profile we can perform the sweep operation. So, as you can see, the sweep operation is also very useful because we can create a solid from a profile of any shape. The pipe operation allows you to create a solid of a regular shape, and we can also do this with the sweep operation. However, in the case of sweep operation, we can create a solid from almost any profile. So, this operation in some cases can be very useful, and in some cases it can produce really interesting results. Now we will move on to discussing Boolean operations, that is, operations that allow you to subtract one solid from another or combine several solids into one. First, we will create a few simple example shapes. Here we have commands that allow us to draw a sphere, a cube and a cylinder. And let's create a sphere. We select this command, specify the center of the sphere, and by pressing the Tab key we can set a specific diameter for the sphere, then click OK. This way we have created a sphere with a diameter of 50 millimeters. And when it comes to creating a cube, we have a command that allows us to create a cube from a corner. We specify the corner of the cube, and by pressing the Tab key we specify the side lengths of the cube and press Enter to confirm. And now we can specify the height of the cube. The center box command works similarly, except in this case we specify the center point of the cube and then proceed the same way, specifying the side lengths and height. We also have a command for creating a cylinder. We specify the center of the cylinder, press Tab key, enter the diameter and then enter the height of the cylinder. So as you can see, we can also create these basic shapes, and using these shapes I will quickly show you how Boolean operation works, that is, how we can subtract one solid from another. First I will move the sphere. I select the sphere, switch to solid selection mode, select the sphere, activate the move command and move this sphere roughly here. Okay. The sphere and the cube are two separate solids, and using the Boolean operation, for example, we can remove the shape of the sphere from the cube. And to do this, while holding Shift, we select these two solids, and when subtracting solids, the order of selection is important. First, we select the solid we want to subtract from, and then while holding Shift we select the solid we want to subtract and activate the Boolean operation. We can activate this operation by pressing the Q key on the keyboard, and here by default the diff operation is selected, and if we now click OK, we have created a shape that was formed by removing the sphere from the cube. And as you can see, the sphere has been removed from the project. I will now press Ctrl Z to undo this. And again, I select the cube, then holding Shift I select the sphere, choose to Boolean operation, and here we have an option called Keep Tools. If we check this option, the sphere remains in the project, but the sphere shapes is removed from the cube. So as you can see, this is a simple operation, and in this way we can subtract one solid from another. If you wanted, for example, to combine two solids, here I will select the cube and move it roughly here. Okay, now the cylinder and the sphere are separate solids. Holding Shift, I select these two solids, and for joining solids, the order of selection doesn't matter. I press Q and we have the union operation, and we can also keep the source solid in the project. If we click OK, the sphere remains in the project and the cylinder is joined to the sphere. I press Ctrl Z to undo this so that the sphere and cylinder are separate solids again. And as I mentioned, when joining solids, the order doesn't matter, and it doesn't matter if we are not using the Keep Tools option. In this case, I subtracted one solid from another, Ctrl Z again, and now I select both solids, activate the Boolean operation, choose union, and the order didn't matter. Pressing Ctrl Z again, and now I first select the sphere, then the cylinder, choose the Boolean operation, check the Keep Tools option and click OK. Now the cylinder is the solid that was added to the sphere and it remains in the project, while the sphere has been merged with the cylinder. This means that when using Keep Tools during union, the order of selection matters. So that's how this simple Boolean operation works, and these operations are really useful in many cases. In 3D modeling in Plasticity, Boolean operations are used very often. Now I will show you a practical example using what you've learned so far. Let's create a rectangle of any size. It could be a square. Now let's create a line along the axis, something like this. Okay. Let's use the sweep operation here. So I choose sweep using the Shift+P keyboard shortcut. I select this line as the path. Here I use the twist parameter. Let's enter 200, and for scale, let's enter 0.1. Okay, and we've created a solid like this. Now I switch to the top view. Here, let's create a rectangle. Something like this. Okay, and based on this rectangle, we will create a solid. But first, let's hide this solid and the flat geometry, so we can select the entire rectangle. Now I turn the visibility of the solid back on, and here let's create a box so that it is taller than this solid. Okay, now let's use the mirror operation to create a mirrored copy of this solid. Select this operation, click this gizmo so that the solid appears on the other side. Click OK, and now we have two such blocks. Now we will subtract the shape of this solid from these blocks. I turn on the visibility of the first block, select the block, then holding Shift select the solid, press Q, make sure div is selected and check Keep Tools, click OK. And now hide this solid, turn on the visibility of the other block, and as before, select the block, select the solid, press Q and click OK. Now I hide this solid, turn on the visibility of the second block, select this block, press G and move this solid along the x-axis by any value. And in this way we created something like this. And as you can see, with literally 1,000 clicks we created such a project. Overall, Plasticity is a great conceptual design system where we doesn't necessarily care about precise dimensions. Of course we can do that, we can design elements with precisely defined dimensions, but in my opinion Plasticity works better for design where precise dimensions are of secondary importance. What matters more is maintaining the overall proportions, and we want to quickly create a shape. In the previous example, I showed you the mirror operation quickly. Now we will go over this operation in a bit more detail, and it can be applied to both flat geometries and solids. First, I will show you it on flat geometry. I will create a circle of any diameter here. And now I want to get its mirror on the other side of the y-axis, and to do this we activate the mirror operation. And now we define the mirror plane. Since I want the circle on the other side of the y-axis, I click here so that the mirror plane passes through the y-axis, and this way the circle appears on the other side of the y-axis. And by dragging this gizmo we can move the mirror plane along the x-axis. That's exactly how the mirror operation works. Now I will create another shape, for example here. Select the shape, activate the mirror operation. We can activate it using a keyboard shortcut and then define the mirror plane. This is how the mirror operation works. Okay, we can also perform this operation on solids. The solid is selected, I activate the mirror operation, and as you can see, the preview shows the mirror plane. That's how it works. As for the mirror plane, we can define it freely. Here I will draw a line. I select the solid, activate the mirror operation, and as you can see, by default we can define the mirror plane based on the coordinate system planes, but we can also have the freestyle option. I press the F key, and now I have to specify 2 points lying on the mirror plane. Here I will use points from the line, and now the line serves as the mirror plane. We can also perform a mirror operation in such a way that we create a solid, for example a cube. Inside this cube I will create a feature. And OK, and I want to get this feature on the other side of the y-axis, and to do this I select the solid, activate the mirror operation and define the mirror plane. Here we defined the mirror plane in this direction, but let's click this gizmo and see what happens. When I click OK now, 2 solids are created. These solids were split, but I will press Ctrl Z to return to when there was just one solid. I select the solid, activate the mirror operation, choose the mirror plane, and here we have the union option. I press Q, click OK, and in this way we have mirrored the feature that was already on the solid, and now we have it on the other side as well. This can be useful in some cases. And when it comes to mirroring, we can also do it so that I select the solid, activate the mirror operation, and as the mirror plane, I can select a feature on the solid itself. Here I created the mirror so that the face of the solid serves as the mirror plane. And we can create 2 separate solids or press Q so that the solids are joined together. And this is how, using the mirror operation, we can create next solids or next parts of a solid. Now I will show you another interesting and simple operation, the rectangular array. This operation allows you to create copies of a solid arranged in a rectangular pattern. It works like this. We have, for example, some solid. Here I will start by creating a cylinder of n dimensions. We choose the rectangular array command, and now we specify the direction of the array. Notice that we can set it freely. For now, I will set the array direction along the x-axis. Next, we can change the parameters of this array. We can change the array length and we can change the number of elements. We can also define the array in the second direction. Here, let's first increase the number of instances in the second direction to, for example, 5. Now we can also set the length of this array in the second direction. Click OK, and as you can see, in just a few clicks, we have created next copies of this solid. All of these solids are visible in the outliner, and sometimes it can be useful to group such solids into one folder. If we keep creating more solids, all of them will be added to the outliner, and at some point it may simply become messy. That's why it's sometimes worth grouping solids into folders, and to do this we select the solids we want to add to the folder. If they are deselected, you can select them in the outliner one by one while holding Ctrl key, or you can select the first one on the list, hold Shift and select the last one, or you can switch to solid selection mode and use a selection window in the Workspace. Now, to group these solids, click this button and they are now in a single folder. Now, if we create another solid, it will be in a different location in the outliner and won't clutter the view of the grouped ones. This can be very useful. For now, I will delete these solids. I will create another solid, a rectangular box. I will specify exact dimensions, for example, 200 by 70 millimeters. And a height of 15 millimeters. Now, on the top face of this solid, I will create a construction plane and draw next shapes. I will do this by first drawing a circle in the corner of this solid, a circle with a diameter of 10 millimeters. And now I will move this circle along the x-axis by 10 millimeters and along the y-axis by minus 15 millimeters. And click OK. Next, I switch to edge selection mode, select this circle and choose the mirror operation. I will create its mirror copy so that's on the opposite side. Now I select the line drawing command, snap to the edge of the circle, then snap to the other circle where the tangent snap appears, ensuring the line will be tangent to both circles. And I right-click to finish drawing. The line is now selected. I choose the mirror command again, press F to activate freestyle mode, and specify 2 points for the mirror line, simply selecting the centers of the circles, so the line is mirrored to the other side. Of course, we could have drawn this line directly, but here I just wanted to show you the mirror operation. Now I activate the trim command and trim these circle segments. At this point, these shapes are 4 separate lines. This doesn't prevent us from selecting the enclosed area, but if you want to join them, select the geometries you want to merge, either by holding Shift and clicking each one or by using a selection window, but be careful not to accidentally select other edges. Since we have only 4 here, I'll just click them individually, and to join them, activate the join operation using the J key on the keyboard. Now they form one geometry. In this case, joining wasn't necessary, but in other cases it might be useful. Now I switch to face selection mode, and from this area I will create a solid by extruding it to the height of the main solid. I do this by grabbing the gizmo, but I want the extrusion to be added so that it exactly meets the lower face of the main solid. To do this, I hold Ctrl key and hover over a feature on the bottom face so that its height is matched, and then I release the left mouse button, release Ctrl, and the extrusion is added to the feature. Click OK and the solid is created. And now, based on this solid, we will create a rectangular array, but this time only in one direction. The solid is selected, I choose rectangular array, and as you can see, parameters for the second direction are also available, so I set that count to 1. Now we set the rectangular array direction this way, and for the length, note that the center of the first solid is offset 10 mm from the edge, and I want the center of the last solid to be offset 10 mm from the opposite edge. Since the total block length is 200 mm, I set the array length to 180 mm. It's 200 minus 10 from one side and minus 10 from the other side. And for the number of copies, I enter 8 and click OK. Now I want to subtract these solids created in the array from the main block, and to do this I must first select the block we will subtract from, then while holding Shift select the solids to subtract. As you can see, selecting each one in the workspace could be tricky. So we can also do it in the outliner, first selecting the base block, then holding Shift to select all the other solids. Or we could first group these solids into a folder, rename it if we want, double-click the folder name to change it, and then, when performing the subtraction, select the base block, expand the solids group, and Ctrl-click the solids item in that group to select them all at once. Then we activate the Boolean operation, confirm that div is selected, and click OK. Now we have created slots in the block. I'll press Ctrl Z to go back to having just one solid. The rectangular array also works on features of a solid. For example, if we subtract a small solid from the large block, then we can select the faces of that slot, holding Shift to select multiple faces. Activate the rectangular array command and, just like before, create a rectangular pattern based on features instead of whole solids. And that's how the rectangular array operation works. Next, I'll show you the radial array command. Another simple, interesting and useful operation is the radial array. This operation is similar to the rectangular array. A radial array allows you to create additional copies of a solid or selected features of a solid arranged in a circle. In other words, you can create extra copies around a center point. Here's how it works. I will create a cylinder of any dimensions, just like in the previous example. Now I choose the radial array command and specify the center of the radial array. And now copies are created around the circle. Here we can set number of copies and angle over which they are distributed. By default, the angle is 360 degrees, but you can enter a different value to place the copies over an arc. There is also a number parameter that lets you define how many repetitions of the array you want, and a step field where you set the offset distance between subsequent arrays from the first one. As you can see, in just a few steps you can add multiple copies of a solid. And just like with the rectangular array, you can also create a radial array based on features of a solid. I'll create a cylinder, for example 100 mm in diameter and 10 mm in height. Now on the top face of the cylinder, I'll draw a circle with a diameter of 10 mm and move it along the y-axis by -10 mm. I close the temporary construction plane, and with arrays both rectangular and radial, we can also base them on flat geometry. I select the circle geometry, choose radial array, and as the center point, I select the center of the cylinder. I'll change the number of steps to 1, and now, based on this flat geometry, we have created a radial array. Next, I'll hide these geometries. Using Shift, I select the first and last geometry on the list to deselect. Then click the eye icon for one of them to hide them all. And just like before, we can also do this directly with a solid. I create the solid, holding Ctrl so that the extrusion goes down to the lower face of the cylinder. The solid is created, and now I can make a radial array from it. And we have additional solids created in a circle, and just like before, we can subtract them from the main cylinder using a Boolean operation. If I undo back to before the array, I can also subtract the small cylinder from the large one first. And then use the features face to create a radial array. So the operation works both on solids and on features. As you can see, it's a simple tool, but one that can greatly speed up 3D modeling in some cases. When it comes to arrays, there is one more type, the path array. This is also a very useful operation. First, I will create a path using a spline, something like this. Then I'll create an example solid. Here you can see the circle is drawn in the default plane, but by pressing V we can rotate the plane. Okay, we have our cylinder, and now we can create an array of this cylinder along the path. The command is curve array. We select it, then select the path, and here we can set the number of elements. And the scale parameter allows us to resize them so they get, for example, smaller along the path. And the extent parameter lets us lengthen or shorten the path coverage. And that's how arrays work in Plasticity. In this example, I'll show you another useful thing in 3D modeling with Plasticity. I'll start by creating two cylinders. The first cylinder will have a diameter of 40 mm and a height of 10 mm. Okay. The second cylinder will be created so that its center is placed here with a diameter of 15 mm. And for the height, as you can see here, the positive direction is downward, so we need to enter a negative value, and let's enter -50 and press enter to confirm, and now we have our cylinder. Now I switch to face selection mode, select this face, and the push face operation is activated. If I move the gizmo, I can change the position of this face. I press escape to cancel, and when a face is selected, I can either cancel push face with escape or choose another operation from the list. For example, here I select extrude command. And if we add an extrusion, we can either extend the solid or create a new one. First, I'll set the extrusion height, press D, then type 5, and then press enter to confirm the height. And now press B to make it a new solid. And click OK, and we've created a new solid from a face of another solid. Now I'll hide the larger cylinder. Here, for example, we can enlarge this hole slightly. Push face is active, and we can increase the hole's diameter either freely or with an exact value. I press D, enter -1, hit enter, and then enter again to confirm. And similarly, I can do this with this other face, this time reducing the diameter. I press D, enter -1, hit enter, then enter again to confirm. So from a solid's face, we have created another solid. We can duplicate such a solid, for example, with the Shift+D shortcut, and notice that this automatically activates the move command, so we can place the copy where we want. The same works with Ctrl+C, Ctrl+V, which also lets you move the new copy right after pasting. The main point here is that a solid's face can be used as geometry to create a new solid, something that's very useful in fast modeling. Once we have a few solids in the project, we can switch to the Assets tab and now select a solid, then select a material for it. Switch to render mode, and you can see that each solid can have its own material. For each material, we can activate it and adjust its parameter, including scale, which can help fine-tune the appearance, especially for small elements. In some materials, the change is clearly visible, in others, less so. If you want to make a simple visualization, you can hide the grid and coordinate system and also turn off X-ray mode so hidden edges are not visible. This way you have a clean, simple presentation of your model.